Welcome to the Week 12 lecture for Microprocessors and Robotics. This week we're going to look at the different components of robots a little bit more in detail. So those components that we're going to be looking at include the drive system, the controller, the program, the arm or the manipulator, the end effector, and the sensor. So all of those are typical components that would go into most, if not all, robots. So we'll break those down in a little bit more detail and understand all of those pieces that fit together to make a complete system, the complete system of a robot. So here's a list of all of those components I just mentioned, the 6 main ones, and here's a diagram that includes all of those components except for the last one because it's really hard to depict in a diagram. So we'll go through and look at all of these in more detail, but just to point out where each of these are. So the drive system is what is supplying power to the robot. So that's over here noted as a power supply. 2 is the controller. That's what is communicating with the robot, going back and forth with commands and feedback. We can see it here between the robot and then external commands. We also have our program. So this is kind of best shown over here. This is how we're getting the program to the controller. And then we have our arm or our manipulator. And this is a lot of what we covered in last week, was looking at the different kinds of arms, our manipulators essentially, the different configurations for those. And then we can have different end effectors. So whatever is on the end of the arm, we have a lot of different options there depending on what application we're doing with the robot. And then it's not shown here because it's a little bit difficult, but number 6 is sensors, and that would include any sensors that the robot needs to function, to receive information generally. So we'll look at some examples of sensors in a little bit. So those are all of the main components that are going into most robotic configurations, and now we'll kind of get into each one of those. So the first part of a system that we'll talk about is the drive system. So this is what powers the robot, and this is what is driving that movement. So it's not necessarily controlling it and that it's telling the robot what to do, but it is providing power for the robot to carry out any actions that it's told to. So a drive system is typically one of 3 types. It is usually electrical, pneumatic, which is air-powered, or hydraulic, which is a fluid-powered system. So drive systems, here's kind of the main questions concerning drive systems. They control the speed of the arm, so how quickly that arm can move, and they also control the strength of the robot. So you might remember last week we talked about how there could potentially be some trade-offs in like servo motors and stepper motors between speed and torque. So those are essentially what we're seeing here. Torque we can kind of consider to be potentially the strength of the robot. So a drive system is responsible for those 2 things. Sometimes you could have the best of both. It just depends on kind of what grade of a system you have. So sometimes you will experience trade-offs between speed and strength in a robot. It just depends what's involved in your drive system to control that. There's also the dynamic performance of the robot, so how it's moving around. The drive system can help control that, the kind of fluidity of the movements. And then the application type is going to be, the drive system is going to be dependent on that. So just like we talked about how for some applications servo motors might be best and for others a stepper motor might be best, the same thing applies with drive systems. So for some applications an electrical drive system might be the best option, whereas for another it could be a terrible option. So we'll get into that in a little bit more detail. We'll look at some of the advantages and disadvantages for each of these system solutions and kind of learn some of the ins and outs. The first drive system that we'll discuss is the electric drive system or the electronic drive system. So its name kind of gives a clue as to how it's powered. The system is using electric motors to actuate the joints of the robot. So that just means that whenever it is moving the robot, electric motors are powering that. These electric drive systems typically have high accuracy, so they can be very precise. They can move the robot to a precise location because of the precision of the motors. And they also have a high degree of repeatability. So what that means is if you are targeting X right here in the middle, so accuracy means that every time you'll come close to X, right? Accuracy is kind of how close we're getting to X. So all of these that I just made would be considered highly accurate relatively. And if your robot was out here, that would be inaccurate, right? So when we talk about repeatability, repeatability is the ability to be consistent. So a robot may be repeatable. It might consistently hit the same spot over and over and over. So this might not be very accurate, but we do know that the robot will always be in this spot. So that kind of helps. Sometimes we can adjust things around that. Ideally, you do want high accuracy and high repeatability for a lot of applications, but just to differentiate the two. And then so a low repeatability would mean that the robot is kind of all over the place here. There's not really any telling where it'll end up. So it's in this general vicinity, but it has a wide range of where it actually is. So just to help us distinguish between high accuracy and repeatability, electric drive systems are typically very low cost, they're easy to maintain, and they do usually take up a lot less floor space than a pneumatic or a hydraulic drive system. They can be very, very compact. So a pneumatic drive system is air-powered. Pneumatic references an air-powered system. These are typically limited to smaller robots and simpler locations. They don't always have a lot of power behind them, but just like the electric drive systems, they are easy to maintain. And then a hydraulic system will use hydraulic pistons. So whenever we refer to a hydraulic system, hydraulic means that it involves a fluid of some type. So a fluid is involved, and this typically gives us a little bit more power transfer than a pneumatic air-powered system would. So that gives us a higher strength of the system. It's a much, much stronger system. It's good for if you need really high power, if you need a robot to be lifting really heavy capacities or managing really heavy weights. The hydraulic system has the capability and the stability to do that, whereas an electric system certainly wouldn't, and a pneumatic system would not either for those heavy, heavy applications. A hydraulic system also can have really high speeds. One of the drawbacks of all of these features is that typically these systems are a lot more larger. That should kind of make sense because they're much more powerful. It's harder to get them down into a really compact size. So we need that larger size to support the higher strength and the higher power that comes with the hydraulic system. Now that we've covered the basics of each drive system, I want to get a little bit more into detail on the advantages and disadvantages of these, so you can kind of get an idea of the environments that these would play well in or environments that these would not be a very good match for. So in an electronic drive system, we talked about that they can have high accuracy, they can have high repeatability, and they're really good at velocity control, so starting and stopping and accelerating properly. Electronic drive systems are really good for those things. They're also economical. I don't think I moved that bullet point over to here, but we saw it before. The maintenance on these systems is easy. They typically don't overheat. They have a low temperature dependency, so what that means is they can operate in a decently wide range of temperatures. The temperature doesn't have to be within a too particular of a range for the drive system to function. There are some limitations because there's electronic components involved, of course, so those can't get too hot or too cold, but for the most part, their functioning range is pretty broad. These systems are also quieter, and they will function at a 20 to 60% efficiency. Of course, like with any system, there's some drawbacks. So I alluded to this in the last slide when I was talking about hydraulic systems, but our electronic drive systems are for much lower loads. They can't exert large forces or move too fast. So they have really good velocity control, which means when they're speeding up and slowing down, they have really good control over that, but their max speed isn't as high. So they just essentially, they don't have as much power. So they can be really precise, really cheap, really easy to maintain, but they're more for lightweight applications. Another point that reinforces this is that under shock loads, they don't hold up well. If you think about it, right, when you're shocking electronic components, that's never a good thing. Sometimes they can have a difficulty holding a position. So if you think about maybe a robotic arm has to hold a load in a particular position for a long amount of time for some other operation to happen, we can experience some slip in that position. So they might get there really accurately. It might be a really repeatable position, but they might experience some slip if they have to stay in one spot for a long time. And they also have a little bit of a higher initial cost. So overall, the cost is lower because you're not paying for continued maintenance and upgrades and things like that with these systems, but they do have a little bit of a higher initial investment. So overall, they can be cheaper as a whole over their lifespan, but that does come with a higher initial cost. Next, we have some of the more detailed advantages and disadvantages of our pneumatic or air-powered drive systems. So one of the advantages of these are that they're simple, right? Pneumatic, they're air-based, so it makes these a much simpler system. There's not a lot of electronic components like with the electrical drive systems, and we're not dealing with a hydraulic fluid like in a hydraulic system. Compared to our electronic drive systems, pneumatic one has a lot more force and speed per size, so these could be a little bit more powerful. There also is a lower investment cost. So remember I said that an electronic drive system has a really high investment cost, although the maintenance is a little bit lower. Pneumatic drive systems are almost the opposite. So it's it's relatively a low cost to get this system set up. But over in our disadvantages, it does cost a little bit more to maintain. They do require some more maintenance. They do resist overheating. They're pretty resistant to that in moist environments. That's usually not a problem with these drive systems, and they are explosion and shock proof, mostly because they're pneumatic powered. So that gives these systems a lot of advantages. There are some disadvantages, as I alluded to before. These, they cost more to maintain. They're not as efficient as some of the other systems, so they can produce more force and speed for their size, but you are still potentially losing a lot of power with the drive system. So they're not always very efficient. They also have to be appropriately sized. So what that means is you have to make sure that you have enough of an area to fit these in. Essentially, they can be a little bit bigger than an electronic drive system, so they have some larger size requirements. And then you have to make sure that the drive system is sized up to account for that loss in efficiency. They also need some additional components, so you have to add regulators and some more valves to try to boost that efficiency. And they can, they're subject to air contamination. So that could potentially be an issue with these drive systems and cause more maintenance problems. So like any of these systems that you'll see, there's always some trade-offs. And just depending on the application and kind of what you need from a drive system and what you're willing to invest, pneumatic drive systems are certainly not the worst. They're just better suited to certain applications. Lastly, we'll take a more detailed look at the advantages and disadvantages of a hydraulic drive system compared to the electronic and the pneumatic drive systems. These systems certainly have the highest force or the highest power out of any drive system. The hydraulic fluid really gives them a lot of power. They're also able to be really resilient. So if there's a lot of shock and vibration happening in the environment, maybe it's a really unstable environment, these systems can weather really well. They also have really good power transfer. So they're good at transferring power through the whole unit, although this is separate from efficiency. So the drive system can transfer power really well. That's why they're so high powered and they can have such high force. But it's really hard to get a high efficiency out of these units. They also can have a really good power to size ratio. So I talked about how the pneumatic drive systems, they have to be appropriately sized. There has to be enough space. The power to size ratio on hydraulic drive systems is a little bit better than that. Because they're a stronger system, you don't need as large of a drive system to get the same amount of power if you're using a hydraulic system compared to a pneumatic. I already talked about the shock load, any sort of shock vibration in the environment, they handle really well, and they can also last a really long time. So they can be a really rugged, durable, high-powered system. Of course, we get to our trade-offs, so our disadvantages. If there is a fluid leak in these systems, it can be really hazardous depending on what that hydraulic fluid is and what the environment is. So they have to be monitored very carefully for leaks. Of course, if there's a fluid leak, this can also impact efficiency. That will go way down. And this contributes, along with other factors, into these units requiring a really high level of operator support and maintenance. So that contributes to the cost of maintaining these. If you need any additional parts for these systems, if you wear out a motor, you need a new pump, release valve, anything that's going on these units, those are going to be a lot more expensive than anything needed for a pneumatic drive system or an electronic drive system. Those components can be a lot cheaper to replace, whereas a hydraulic system starts to get really pricey. So the cost of replacement parts and of maintenance in general on these drive systems can be really high. There's also typically lengthy setups involved when you're bringing in one of these systems. There's a lot to them, so it can take a little bit longer to get them up and going. And because they are using hydraulic fluid, they are subject to temperature fluctuations. So depending on the thermal coefficient on that fluid, at certain temperatures, the fluid can expand or it can contract at colder temperatures, and this affects how the drive system functions. So you do have to bear in mind what temperatures these are going to be operated in. If they're subject to like maybe a non-heated, non-cooled factory environment, and somewhere that gets really hot in the summer and really cold in the winter, or maybe they're outside, then that could cause some issues or cause a need for adjustments within the system based on temperature effects. So I think that covers everything for the hydraulic systems. Again, they can be really powerful, really durable drive systems, but they do come with higher hazards and more maintenance. Here's a nice chart that I've included that compares some of the main characteristics that you would consider when you're looking at a drive system for all of our three options, so pneumatic, hydraulic, and electric drive systems. These are all up here. I'm not going to cover all of these in a lot of detail. We talked about a lot of these in our advantages and our disadvantages and our overview, but this is kind of a really great quick reference, a really good reference slide for you to use if you are kind of unclear about the differences between them when they're stacked up beside each other, or if you need to consider basic selection of what sort of drive system that you should kind of start off with looking at. This is a really great basic comparison here. That covers all of our basic information about drive systems. Next, we'll take a look at the controllers that are used in robotic systems for feedback. from an external source, commands from an external source, and then giving commands and feedback to the actual robot. So the controller is kind of the go-between between those. It's kind of like our buses in our microcontrollers and microprocessors. So in a robotic system, the controller is essentially the main processing unit. It's what's controlling the actions of the robot. It's giving the commands. So our drive system provides the power for the robot to carry out the commands that are given by the controller. So if you think about it, the controller is similar to our human brain, right? It's giving our body thoughts and actions to work on. And our muscles are essentially what is controlling, say, our arm to reach out and maybe grab a cup. Our brain is subconsciously telling our arm muscles to reach out and grab it, and the muscles are carrying out that function. So the muscles are like our drive system, in a robot, whereas the robotic controller can be compared to the human brain. So the controller helps the robot carry out whatever tasks are assigned to it. It can take in any information that the robot is receiving from different sensors, which we'll get to in a little bit. So it's inputting information into the controller is processing this information, and it's providing some sort of output for the robot to act upon. The controller can also help the robot to interface with other systems. So this could be other robots, some other machines. It could be even things like the cloud, or potentially your cell phone. So the controller kind of integrates everything and it pulls it all together. And it's processing all of those inputs and providing outputs for the robot. Just like we had three types of drive systems, or three main types, I should say, of drive systems, there are also three main types of robot control. So a controller can be what's called point-to-point. It can be continuous path, or it can be a controlled path. So we'll look at each of those in more detail. In a point-to-point path, the robot is typically receiving input as to the start and the finish point with nothing in between. So a robot might be told to start here and to end here with no instruction for movement in between those. So the robot would record the point of these yellow X's, but it would determine the path in between them. So the controller would figure out, usually it's the shortest path. So you wouldn't see it do kind of this. What you would see if the robot was controlling its own path, or rather determining the path between 2 points, is it would take the most direct route between them. So as you can see, this is best for straightforward, simple movements. We don't want any obstacles in the way. So if we would have an obstacle, let me add it here. We'll say a box is in the way between point A and point B. When the robot is calculating its move from point 1 to point 2, it doesn't recognize that there's a box in the way. And so what's going to happen is it's going to hit the box on the way to point 2. There's going to be a big crash. And so it doesn't know that it needs to navigate around the box. Now you can potentially add a third point for the robot to go around the box. So it could navigate to this point first and then to the second point. So that's an option. It gives a little bit more flexibility. But you can see this is still a very simple path. So if a robot has to squeeze through a tight space or navigate around a lot of obstacles, it's going to be really hard to use point-to-point control. But if you do just have simple movements like this, it can be really quick and really easy to program that robotic movement using point-to-point control. So again, in point-to-point control, you are just giving the robot these points, which are our yellow X's. You're saying you need to hit these points. I don't really care what the path looks like in between them. Just make sure that you're going to these points that are commanded. A control path that's a little bit smoother than point-to-point is a continuous path robotic control. So here, the robot is recording those in-between points. So if we start out with point 1, we have point 2 down here, and there's a box in the middle, we're kind of walking the robot through these steps. So we wouldn't only give it the points, but we would be manually moving it between the points. So we would start the robot out here. We would slowly move the robot the first time we're programming. We might say move around this box, and then we would move it to this endpoint. So we haven't told the robot to go to this point, and then this point, and then this one, and this one. We haven't programmed those in as points. All that we've programmed in are points 1 and 2. But in a continuous path, the robot will remember these points to help map out the path. So it can break it down into smaller geometry pieces to help it navigate around simple obstacles and things like that. So this is a little bit more of a precise path control than point to point. Then we get even more complex in our control options with a controlled path. So a controlled path, instead of trying to kind of map out this blocky motion around an obstacle, we can add in a smoother line. And so this really helps smooth out the program. Let me kind of draw my start and end points here. Put the box back in, our obstacle. So here, what we can do is the robot, let me start this again. So it can do a more complex geometry. So if we were to try to move this robot manually around the box, it could be very clunky and not efficient. If we tried to go in a circle, it might look like this with a lot of little steps, and we would have a hard time doing that. But with a controlled path to path, the robot is able to use complex geometries. So my drawing is still not the smoothest here, but you can imagine a much smoother geometry. It can calculate the radius of this arc, and it can move it in a smooth fashion. So instead of kind of the jerky, halting fashion of the green line, the robot would move in a much smoother fashion of the blue. It can kind of smooth out this geometry. So this gives us really good accuracy along the path. We're not trying to manually move it to each tiny point to navigate it around an obstacle or in the way that we need it to move. It can take the path that has been programmed into it, and it can smooth out that curve, or what can happen is even in the programming software, you can program the robot itself using this smoother geometry. So you're not required to manually move the robot through the steps. You can go through software. If any of you have ever been involved in machining, like CNC machining, then you know that you can kind of create a CNC code that can build in arcs and things like that. Mastercam is one of those machining programs where you can build your path. You can add in all sorts of straight lines, arcs, different geometries, and get really precise curves. So the controlled path is certainly a lot more precise. It's a lot more accurate and very steady. And sometimes you don't even need to map out all of these geometries. If the robot is equipped with certain algorithms, you can give it the start and the finish point, for example, of this arc, and it can calculate the arc between these points. So controlled path is a lot more precise. It's a lot more precise way to control your robot. Here's an example of a robot performing an application. It looks like they may be printing something or possibly spreading a glue down on a sheet. And so when we think about what kind of path would we need for this, we think point to point would certainly not be a great path. The robot, if we told it to move point to point, would just start here and go in a straight line to here. Otherwise, we could program in a bunch of tiny zigzag points, but this looks like a smoother line. So we know this probably isn't using point to point. This maybe is using a continuous path, but that would be really hard still to achieve that smooth squiggle. So a continuous path would look kind of rough and uneven. We might have a hard time getting the robot to follow this really nice and neat pattern. So this robot is most likely using a controlled path to get this smooth, controlled, nice and even distribution of glue or printing, ink, whatever this may be. So this application here would need a controlled path programming style. Now, this application, we have some robotic arms painting these cars. To keep things simple, we'll just assume that this arm here is just responsible for going back and forth and painting the hood. So we probably don't need a controlled path for that. We probably don't have to get too precise. We might, but this is probably pretty simple geometry to just do, I'm sorry, the roof of the car, not the hood. To do the roof. So we might be able to use point to point, maybe if we shut these sprayers off, or if overspray is not really an issue, we could tell the arm to go to this point, and then go to this point in the back, move over a little bit, sweep over here. And so point to point might work for this. Or if we wanted things to be a little bit smoother, we might use a continuous path. Maybe if we wanted the arm to kind of curve around these sections here, but it doesn't really matter if it's a smooth motion because it's off of the roof, that would work. So potentially any of these controller types could be used, but most likely it would be a point-to-point or a continuous path would be good enough for this application. Now, if we got down into maybe a more complex body panel where overlap is a much bigger deal, it's much harder to go off the panel maybe, then we might need a very controlled path. But for something like this, that's a big wide open area, point-to-point or continuous path would probably work just fine. Lastly, we have a robot that is unloading 2 drills from this machine. And so the best way to do this would probably be a continuous path, so not a controlled, but a continuous, to where the robot would be in the machine. You could grab a color that shows up a little bit better. So the robot would be in the machine. We might tell it come up here, out here, and then down here into this tray. And so point to point might work if there's not too many obstacles here. We might be able to have the robot do this basic motion. Or if there's a couple more obstacles that we might need to twist this arm around very carefully. Then point to point could result in a crash. So if we need to start twisting the arm and kind of very carefully back the robot out, then a continuous path might be more applicable so that we can make sure that we're navigating those obstacles. We might not need a controlled path necessarily. That might be overkill. I think a continuous path would work just fine here. So that we're kind of navigating through this tight space, but it's still very basic linear motions. So we've looked at our drive systems and our different options for control. Now we'll look at some of the options that we have available to program a robot. So back in the early days of CNC, or rather kind of automated machining, they were actually programmed with little punched slips of paper. So you would punch in different holes in different locations to stand for different machine positions. You would punch these into a roll of paper, and then the machine would read this roll of paper as guidance for where to go. Luckily, things have since become very much advanced from these rolls of paper. So if you make a mistake or if you need to make a slight change, it's a lot easier now. A lot of the programming methods are computerized, and they're a lot simpler. So we'll take a look. The first programming method that we have is the teach pendant. Some of you may have seen this in the ATC lab. There is a kind of a robotic arm there that can be programmed with the teach pendant. So with the teach pendant, this is a handheld unit that you can use to move the robot to a position. You can save that position in the code, and then you can move it to the next position, save that position, and continue. So once you've moved the robot through all the steps that you would like it to perform, you can then run that code back at a faster speed and the robot can step through those steps. So we'll take a look at what that looks like on the next slide. I have a video of that. So here you can see this man is carefully moving the robot to each position that he wants it to go to, and then he's saving that position in that little handheld device that he has, which is called a teach pendant. So here he's rotating the robot into the position that he needs. He'll save that position and then move on to the next. So this can be a very time-consuming way to program if there are a lot of steps, but it also can be useful to be right there on site if you need to navigate the robot around any obstacles, or move it to a very specific location that you don't have documented necessarily. A teach pendant can be a really good way to do that. So now we'll see the robot go through all of those commands that he's programmed from start to finish automatically. In just a second. He's moving it back to the home position right now where he wants the robot to end. That's where it'll come back to. And then it'll play through. So you'll notice how it's very quickly moving through those positions that took him a long time initially to program in, but it is hitting each of those points that he had programmed in there. Some of the advantages and disadvantages of the teach pendant are covered here. This is a pretty basic system, so there's not a lot of either. The advantages is that teach pendants are widely used for a lot of different kinds of robots and machining, so they're very common. You can get decently precise positioning without a special reference point. So in the video that we just watched, if that hole didn't have a specific X, Y, and Z reference in space, right, it would be really hard to measure exactly where that is to give the robot a coordinate. In that case, it was much easier to just move the robot into position visually to see that kind of fit. And so it was a lot easier in that case to get it into that specific positioning. Likewise, if you need to move a robot very close or just touching a specific surface, that might be really hard to program if you don't know exactly where that surface is in space. So with the teach pendant, what you can do is you can slowly ease that robot closer and closer and closer to the surface until you get it exactly where you want, and then you can teach that point in. So this method is really great for simple movements like that. It really does have its advantages for simple programming. The biggest disadvantage when using a teach pendant is that the machine has to be down while you're programming, and that programming takes so much time. So as you saw, it took that man quite some time to program the robot to execute that sequence when it actually took the robot very little time to execute. So when you're talking about a factory, when you need the machines to be down, meaning they're not producing any sellable products while you are programming, This can create a lot of pressure. It can create a loss of money because the machine is essentially it's not making money for the factory while you're programming. So that's certainly a disadvantage. Everything has to come to a stop while you're programming, and it can be very lengthy to do. Our next programming method is offline programming. So what this means is that while the robot is somewhere else, you can program it usually through software on a computer. You don't have to be right at the robot. The software will usually give you a mock-up of the robot, the space that it's working in, and you can use this software to program the robot's actions without physically being at the robot like you need to with a teach pendant. Of course, the biggest advantage to programming offline is that you can be offline. You don't have to physically be there. You can be nice and comfy in a chair at your desk. There's not as much of a rush to program right away. There's no downtime involved, so the robot can be working on something else while you're creating a new program for it. There's also a lot of software that's really intuitive and easy to use. So I briefly talked about Mastercam earlier. If you've ever used a CNC, you might be familiar with that. That's a really common one. There's a lot of other different softwares for things that we might not think about as robots, but things like an EDM machine, a mill. CNC is really the most common. So there's the main ones there. There's the lathe. Lathes can be programmed with software. So there's a lot of different softwares, a lot of different things that you can program with those softwares, but they make it really easy to work out all of the details of essentially your code. Another advantage is that you are able to test multiple approaches. So usually the software includes a simulation. So before you go out to the machine to test it, you can simulate it with the software and get a really good idea of what the robot is going to do. So this allows you to test multiple approaches. If you're not sure about the best way to program something, you can take your time, you can save a couple different iterations. And so that can be a big advantage. It also can be a lot faster to program in the software. There are two main disadvantages to programming offline. The first is that it's really hard to represent with perfect accuracy the robot and the environment that it's in. So it can be really hard to define a work envelope, or if something is in that work envelope, if you have a table in there, you would have to get really precise with measuring exactly where is that table, how high is that table, and replicate that in your simulation. So with a teach pendant, you can see everything in that physical space and you know the exact relation, whereas in software, it can be a little bit of a guess. You might have to move things around a little bit to adjust. So oftentimes we can get close with software for robotic programming, but sometimes we may have to tweak it a little bit, bring the arm down a little further, out a little further to really get it where we want it. Sometimes there can also be simulator issues with software, so unfortunately nothing is perfect. Simulators certainly have their value. They're really great. They can catch a lot of issues in your program, but they don't always catch everything. So it's really important when you're using simulator software that you go through the program usually very slowly the first time to kind of vet out the steps that are happening. And then once you've verified, of course, you know the program's good and you can run it. But there can potentially be some issues or some inaccuracies in your simulation when offline programming. But altogether, this is much more efficient. It can be a lot easier and a lot faster than using a teach pendant. The next programming method is a little unique. This one's really interesting. It's called demonstration programming. So this involves physically moving the robot around it could be using a force sensor or a joystick attached to the robot. And so you're manipulating the robot into the exact position that you want. So a teach pendant can be kind of clunky sometimes. You can be limited to like an X, Y, and Z axis, maybe 6 axes. you are a little bit limited in how you're moving things around. So with demonstration programming, you can sometimes get a lot more fluid. You can be a little bit more, you can be precise a little bit more faster. So instead of slowly moving the robot to a point with like a teach pendant, or trying to get it to a point with offline programming and then having to adjust, in demonstration programming, you can just move the robot to the exact point that you need it, and then it's recorded kind of similar to a teach pendant. So I mentioned that the demonstration programming method was similar to a teach pendant, but one of the advantages is that it can be much faster. You're not trying to step it through those little increments. It can also be a lot more intuitive. So instead of trying to figure out what's your X plane, what's your Y plane, what is Z, and trying to get the robot to move in that position, it's a lot easier to manipulate into that position. So it's a lot more intuitive than either of the previous two programming methods that we've talked about. And it can also make programming a lot simpler for complex movements. So in a teach pendant, it can take a lot of work to manipulate a robotic arm, for example, through a really complex, maybe reaching and twisting movement. In programming, even in offline programming, it could take a lot to manipulate the robot through those actions. But in demonstration programming, it's very easy to grab the robot or grab the joystick or perform that movement yourself where you're reaching out and twisting. So it can be a lot simpler and faster. Unfortunately, like the teach pendant, because you're at the machine, it has to be stopped for you to program it. It does create downtime like the teach pendant, and so potentially loss of money like the teach pendant. It is also a little bit less precise. So I said sometimes it can be more precise if you're trying to reach a very specific endpoint or to lightly touch an endpoint. It's great for that, but for other movements, right, as you're just kind of moving through those motions, we're not always very precise. It will be mimicking the human motion. So it may not always be, for example, a perfectly straight line or a perfectly smooth curve. There could be a little bit of wavering that's in there. It's also not great for algorithms. This kind of ties into the precision. So when you're offline programming, the machine can use algorithms to find sometimes the smoothest path or the straightest, the most efficient path. Whereas when you're demonstration programming, the robot doesn't have that chance to find the most efficient path or the smoothest path. It's just mimicking what you've programmed. So in that aspect, it's not great. That is a disadvantage, but demonstration programming is certainly unique, and it does have its place. In conjunction with the different ways of programming a robot, there is always a language associated with that. So you might be using a software to create a program, but ultimately that software is going to output some sort of code. Your teach pendant is going to generate some sort of code. Demonstration programming is the same way. Ultimately, you'll have some sort of program or code that will repeatedly tell the robot what to do. So this can be in a variety of languages. We've looked at some of these. It can be C, C++, Python, Basic, Java, Assembly, MATLAB, and a whole variety of others. So there's a lot of different programming languages that can be used. Sometimes programming languages vary depending on the machine type, depending on the manufacturer. So there's a lot of different ones, and it's kind of like our processor language. Our processor and programming language combination kind of makes up like a regional dialect. It's a similar thing with robotics. So your programming language in conjunction with the controller kind of ends up in this unique combination. So now we've covered half of the components in most robots, and now we'll get to number 4. We'll take a look at the arm or the manipulator of a robot. I did cover these in last week's lecture, so I'm not going to go over all the details this week, but just to reiterate, there are 6 main types of robotic arms. So we have articulated, Cartesian, cylindrical, polar, Skara, and delta. We'll step through those real quick, but if you need that more detailed reference, I would recommend just going back to last week's lecture. Because of the power of online and uploaded lectures, we're able to do that. So there's really no reason for me to go through these in so much detail. After that quick refresh on arms, we'll go ahead and move on to end effectors. So an end effector is essentially a really generic term to encapsulate a huge variety of different things that can be added on to the end of the robotic arm. So what we would kind of call the robotic wrist. So there's a lot of different attachments that we can add for different functions. Usually it is a gripper of some sort to pick things up or a tool to perform some sort of function. So we'll look at some examples of end effectors. Here are some mechanical gripper end effectors, so you can really easily see how these would be used to pick things up, move them around. These end effectors, of course, are designed with the intent of gripping some object and transporting it. Next we have suction or vacuum cup end effectors. These are kind of similar to the mechanical ones in that their function is the same, to pick something up and to move it something else, but these can be a much gentler way to do that. So for example, if you have a body panel of a vehicle, you don't want to grip that with the mechanical gripper. You could risk scratching it or damaging the panel. So suction cups are a really good way to pick that up without causing any damage. I've seen really large sheets of plastic moved with suction cups. That's really easy to move them that way, as opposed to with a mechanical gripper. It would have to be really large. So suction cups, usually you can get away with something that's a little bit smaller, and it's a little bit less damaging if it is a smooth surface item. So that's when these end effectors really come in handy. We also have magnetized grippers. So you might think of maybe a junkyard automatically, kind of the big swinging crane that's pulling magnetic items out of a junkyard, for example. I know that commonly comes to mind. That's in a lot of movies and things. We see stuff like that. But these can also be used for a lot of different applications. So potentially any metal components where the surface finish is not super important. A magnetized gripper may provide a much stronger grip than a mechanical one, or if the surface is not perfectly smooth, it may provide a better grip than a suction cup. If the item's really heavy, it could potentially provide a better grip. Or if you're pulling out a metal component amongst a bunch of plastic, or maybe even if you're looking for metal filings, if you would have some metal filings mixed in with some other components and you needed to get those out of there. For example, you could be searching for metal in a big giant tub of resin. Sometimes we would do that so that the metal didn't go through an extruder. So if metal gets mixed in with plastic, it goes through the extruder, it can really ruin the inside. And so potentially you could use a magnetized gripper to go through all of the plastic resin and pull out any sort of metal shaving. So there's a lot of different applications for these. I included images for some of the main types of end effectors, and the rest I've just listed here because they're really common. I think we can all get a good idea of what they look like. So end effectors can be common tools, things like a welding gun, spray paint gun. If you have a drilling spindle, that could be an end effector, essentially a drill on the end of a robotic arm. It could be a grinder, a torch. Essentially any tool that you can think that would potentially be handheld by a human, it can be an end effector for a robot. Some additional ones would be hooks, maybe scoops, even an adhesive end effector for certain applications. So you can see we really have a wide variety of end effectors, things that we can attach on the end of our robotic arm to perform the task that we need. Now we're on to our very last section of components. The ones that I mentioned are not pictured here, but are very, very important for that feedback loop. We're going to move on to the sensors required for a robot to function. I mentioned sensors a little bit when I was talking about the controller. I talked about how the controller was receiving information from external sensors that the robot had to feed information into the controller for it to process. And so essentially what sensors are doing is they are sending information in the form of electronic signals to the controller. So just like your push button is essentially a sensor for pressure in a way. It's not measuring the pressure, but it's either a yes or no. For a certain threshold of pressure, it's sending that signal back to your microcontroller. So there are a lot of different sensors and inputs that we can use to give our controller for a robot information. So anything about its surroundings, maybe what's going on in the world around it, what's the temperature, what's the humidity, what's the light, is there anything close by? It will let the controller know as well where the robotic arm is at. So think of that kind of closed feedback loop, right? The sensor can tell the controller exactly where the arm is spatially or what's going on around it. So sensors are absolutely necessary for the controller to have that information, to see where the machine is at, what's going on around it, so it can process that information into different outputs. Here's a list of the wide variety of sensors, and this is certainly not all of the sensors. There's a huge variety that can be used. Here's some of the more basic and more common ones. I didn't include pictures because these are typically really small electronic components that are not that exciting to look at, but they can provide input for things like light, if there is sound, temperature, contact sensors, so if something is touching the arm or if something is close by would be a proximity sensor. I can have distance sensing, pressure sensing, all different types. So I won't read everything through the list, but sensors give us a lot of options for the robot to take in information from the world around it and process this into actions. So the acceleration sensor can tell the controller how quickly the robot is accelerating. It can see if it's meeting what it needs to. A temperature sensor may indicate the need to adjust the program for certain things based on the temperature. For example, we talked about the drive systems being sensitive to temperature, so potentially you could program to compensate for that. If there was pressure applied to the robot, it could be compensated or programmed to stop moving potentially, so it's not knocking into anyone or anything. If it senses something in front of it, it may stop using a proximity sensor. So there's a lot of different things we can do with these sensors to make our robots function, and they're a very vital part of a robot for it to function properly and usefully. So that concludes the sensors portion and overall the 6 different components in a robot. That's everything involved there. But before we conclude our section on robotics, unfortunately our very brief section, I do want to cover a couple things about robotics engineering in general. So if any of you are really interested in robotics, you're thinking that might be the kind of engineering for you, I do have a couple interesting facts related to that. Even if you're not, this should be really interesting. So about 5 years ago, there was a poll of a couple hundred corporate executives, so things like CEOs, CFOs, kind of all of the big wigs of a lot of the top companies, and 81% of the people who took that poll said that robotics was the top area of job growth for the nation. So the study of robotics and the development is actually creating jobs. So they can replace simple tasks or even complex tasks performed by humans, but they are still creating jobs in that they need people to program these robots. We need people to set up these robots. They have to manufacture them. We have to maintain them. And so essentially we're shifting our workforce from performing very basic tasks to requiring people with a more advanced skill set. So 21% in this study, it was said that 21% of manufacturing plants will become smart factories by 2022. I think that might be a little bit high. That's approximately 1/5, but there's certainly a movement towards lean manufacturing and becoming much more efficient. And I think a key part of that will certainly be robotics for a lot of plants. The U.S. Bureau of Labor Statistics reported that in the last 7 years, over 100,000 robots were added to factory floors. So they could be doing a huge variety of tasks. Um, they could be CNC machines, they could be assembly machines, things like painting, things like moving different components. But over 100,000 robots were added to factory floors in the last 7 years. And I would certainly expect that curve to get higher and higher as we go on. I mentioned jobs before, how robots can actually help us create jobs, or rather shift where people are needed. And so almost 900,000 new manufacturing jobs were created as a result of automation. So automation is allowing companies to be more efficient, and it's allowing them to kind of reroute their resources so that they can focus on expansion or moving people into other areas where their labor is best used. So they're certainly responsible for creating jobs as well, not just a lot of people like to accuse robots of destroying jobs. So it's very important to keep in mind that they are essentially shifting jobs. So instead of needing people to perform boring, menial labor or boring tasks, we need people to, again, create these robots, help manufacture them, repair them, install them, program them. It's calling for a new labor set. And part of the reason why robots are so important to integrate into factories and why a lot of people are moving that way is that what a study actually concluded that 80% of manufacturers are reporting a labor shortage for production positions. So some of these, even the very basic positions, are open and manufacturers are having a hard time filling them. So of course a robot is going to be much more reliable. It's there until it breaks, right? But it shows up to work every day. It's on time. It doesn't need breaks. And you know, when you have that resource, you have that resource. So when there is a shortage of labor available or people willing to perform those tasks, robots can be a really great way to do that, especially certain tasks that can cause a lot of fatigue, a lot of repetitive motion. A lot of people don't want to do that, or they can't do that for several years. And so for those types of things, robots are really great. They're really helpful to use in those applications. It's also projected that in the next 4 or 5 years, robotic engineers, which is a subset within mechanical engineering, will increase by 5%. So that's a healthy rate of growth. So it's a good field to get into. And again, like I said, we'll also need a lot of skilled technicians to install these machines, to operate them, to program them, and to perform maintenance. So there is a lot of ways to get involved in robotics engineering. Even if you may not be interested in becoming a full-blown robotics engineer, you can still work with them as a technician in a variety of ways. And I thought this was really interesting. So the median annual wage, so right in the middle of all of the salaries for robotic engineers 5 years ago was $83,000. So this, I should update for 2020, it's conceivably higher now, but even 5 years ago, the average wage, or the median, I should say, annual wage was 83,000. So of course that depends on the area, the state, the city, things like that. But as a base overall, that's a pretty competitive wage for any sort of engineering. So it is a really good field to get into. It's a really interesting field to get into that presents a lot of good challenges. This is a short list of tasks that you might be involved in or help in if you get into robotics. So a robotics engineer or even a technician could be involved with integrating robots with different components like welders, controllers, integrating those pieces all together. You could end up looking at mechanical failures, or if there's an unexpected problem with the robot, troubleshooting that and what's going on. There's also a huge variety of the end effector tooling that we looked at, right? So there's all these different end effectors. People have all these specific applications. And so it could be a whole career just designing those end effectors for different applications. You could work to analyze and evaluate different robotic systems, kind of figure out what system is best, design prototypes for new robotic systems, things like that. You could install, calibrate, operate, and or maintain the robots and be really involved with them, very hands-on on a day-to-day basis. You could, from a more research, I suppose, standpoint, step back from the hands-on if you wanted to and do research on robotic technology to find out, where are the new systems going? How can we push the capabilities? So there's a lot of different options within this field to get involved. Some of the more common places to get involved that you'll see, I think especially around Tuscarawas County, and even just starting in robotics engineering, common tasks or common starts of a career involve building, configuring, testing robots, maybe reviewing designs, the calculations involved in designing a robot, looking at cost estimates. That's always a very important piece, is the cost estimates. There are algorithms and codes that need created for the robot to function, so there's certainly a lot of work to do writing those. You could be responsible for planning robot paths or teaching paths to robots. There is also the debugging that's needed of those paths. So some of these different kind of pieces or assignments, if you will, can be combined. So if you're creating a robot path, you're probably debugging it. You might be programming the code, working with the teach path, the teach pendant path, and debugging. You might build robots and test them and approve designs and do cost estimates. But this is just kind of a basic overview of where you can get started. So these are really common. This is really easy to get into, especially if you're in mechanical or electrical engineering. You can dive right into a lot of these applications. And then I've also included some top skill areas. So if you're wondering if you have the skills to do some of those tasks, here's what's some of the top skills that are really needed to get involved in robotics engineering. And these again depend on exactly what part of it you get into. So you might not necessarily need these for the maintenance of the system. You might not need some of these for the design of the system, but here's some just general top skills that can be really useful in this field. So the first one is computer-aided drafting and design. So think like AutoCAD, SolidWorks, Blender, any sort of those 3D modeling programs where you would be designing plans and schematics, blueprints, and coming up with those robotics concepts. The second skill area is being very hands-on and able to build and construct robots. So robotic engineers not only design them, but there are also engineers that help construct the robots. And so they're working with different manufacturing tools, processes, different materials, figuring out how everything is fitting together to get that proper range of motion and the proper physical properties that are needed. So they're pulling together the design and making it a realization. Research and development skills can also be really, really useful. New systems or even redesigned systems need a lot of work put into those designs, and so you need to research what's out there, what can be improved upon. Usually robotic engineers are at the forefront of research and development, so there's constantly research and development going on because this is still a developing technology. And some of these researchers don't necessarily work developing robots, but they can work in academia. So teaching, being a professor, pursuing other research efforts that aren't necessarily related to a particular factory, just general research. But for this, of course, critical thinking, analysis, communication when you're teaching others, those are really important skills to have. So you don't need all three of these skills to get into robotics engineering. These are just some of the really basic kind of summarized skills that can be really helpful depending on what area you're looking to get into. So now we'll review your homework for the week. I've given you a scenario this week to try to figure out. So here's your scenario. A robot is moving the side panel of an automobile from a flat surface to an upright position on a conveyor belt. I've tried to convey this as best as possible in the image here. So imagine on the left, it's laying flat on a conveyor belt and it needs to be twisted so that it's upright and being assembled into the main body. And then the panel has to be held in that position while it's welded in place. So that's the scenario that you need to solve. And I've asked that you describe the best robot configuration for this job. So if we need to build a robot from scratch that suits this application that I've just described, how would we do that? What components would we select? An important consideration that I've given you, consider that the body panel is a medium load weight, so it's not extremely heavy, but it's not extremely light. So you need to analyze what is the best drive system to use, what's the best control method and programming methods, what would we use to move that body panel properly up into place, and why would we use those, what would be the best arm type, what seems like the best arm type. So there should be a couple that you can rule out really quickly. Even if you can narrow it down to 2 different arm types, you can tell me that X or Y would be suitable because. Let me know what type of end manipulator seems like it would work really well to move this body panel, and what kind of sensors would you need. So it doesn't have to be a list of 50 different sensors, but you should be able to come up with at least 3 to 5 different sensors that this robotic arm would need to move this body panel. So I want you to select an item essentially for each of these components, for each part of the robot. Tell me what would be best and why. So we just talked about, for example, the 3 different drive systems, and I even gave you a quick comparison sheet. So you should be able to visit the advantages and disadvantages of those, look at the comparison sheet, and tell me what seems like, with the information that you have, what seems like the best drive system for this application. What control system would you use for this application? What sort of control would you need to move this body panel? What sort of programming methods could you use? And tell me if you rule out a specific method, let me know why. And if you're unsure of your final selection, just note any pros and cons of that, right? So the drive systems, we talked about how all of those have pros and cons. So you could tell me that you're going with a hydraulic system because it has this advantage, but something to keep in mind is that it does have this disadvantage. So I just want you to go through and kind of explain each selection that you would make, explain why you're making that selection, and you should end up with a paper that's between 2 and 3 pages in length. So you should have at least a paragraph for each of these selections explaining why you made that selection. So I want you to essentially pull together the basics of a robot for this application.